Okay, so hi everybody. Um, in previous videos, we talked a little bit about the so-called law of reflection, which is one of the fundamental ways that a trajectory of a light beam can be changed by interactions with matter. This video is going to talk about the other process, which is what's known generally as refraction. The thing about refraction is it occurs as light passes through a material. When we talk about reflection, it's basically something bouncing off the surface of a material, which happens all the time. But many materials allow light to pass through them. For example, glass, plastic, etc. Most forms of materials can at least allow some amount of electromagnetic radiation to pass through. But as we will see, the path light takes as it goes through an object isn't always a perfectly straight line. So, and in particular, as you transition from going from one material into another, as in this picture here showing a light beam going through a chunk of plastic, you can see the trajectory of the light is bent as it passes through. It gets bent specifically again at the interfaces. It goes in straight lines through the material, but can be bent at either surface. This bending is what is known as refraction, and it's another one of these fundamental processes that involves how electromagnetic waves interact with matter. Now, just like the law of reflection did have some fundamental reasons for happening due to the fact that this is an electromagnetic wave, the rules of refraction also emerge from that. Because what we're going to be looking at is how an electromagnetic wave works in matter. Thus far, we've been mostly focused about the properties of how electromagnetic waves work in vacuum. Basically, as a freely propagating disturbance in electric and magnetic fields, that this is a self-reinforcing disturbance that propagates through space at a very specific speed, which is given by the constant c, which is about 3 × 10⁸ meters per second. This c just depends on the fundamental constants in the Coulomb's and Ampere's laws, and so it is basically the same no matter what type of wave you're talking about. Now, when you have an electromagnetic wave passing through matter, you don't just have electric and magnetic fields. You have atoms, which have positively charged nuclei and negatively charged electron clouds. As the electromagnetic wave tries to pass through this material, it will start pushing the positive charge in one direction and the negative charge in the other. This will create oscillations in how charge is distributed, which is just shown here in a kind of cartoon form with the positive charge moving relative to the negative charges, just because that's easier to see. But in general, there is charge displacement. This, of course, will produce its own electric fields that will affect the electromagnetic field associated with the electromagnetic wave. So in this case, we have interactions between charges and the electric and magnetic fields, which will affect how this wave propagates. It can affect its wavelength, it can affect its speed. Now, in practice, what this does is it does affect the parameters of the wave, but it's still a wave. It's still something where there's a spatial variation and a temporal variation. They both are sinusoidal, so it still has a well-defined frequency and a well-defined wavelength. However, the speed at which this wave propagates is now no longer that fundamental constant c, it's a different number, and it's generically represented with the standard letter for speed, v. Now, since this is still a propagating wave, frequency times wavelength is still the speed, but now the product of those two things isn't necessarily that fundamental constant c, it could be a different number. And it is almost always different from c, and in most practical cases we're going to deal with today, and most cases that you deal with in pretty much any situation, V is usually less than C. There's a few exceptions you could do with some pretty interesting materials, but we're not going to get into those today. Okay. Now, so for any material and for any given electromagnetic wave, you can define what this speed is. And you can imagine various ways you might like to measure that. But for even fairly extreme materials, V is still going to be a very big number. You know, maybe not the speed of light, but still many orders of magnitude higher than any speed we're used to dealing with. So people don't usually like writing down these speeds. What they do instead is write down a quantity called the index of refraction. It is an awkward name, but that's what it's called. It is designated with the letter N for reasons, and it is conventionally defined as the ratio of C to the speed. So a thing I'm going to note here is notice that if V gets smaller, N gets bigger, okay? Now, this thing, this index of refraction, note, it's a unitless number. It's a ratio of speeds, so it has no intrinsic units. And it turns out its values are much more manageable to deal with. But what that value is depends on the nature of the material. So like resistivity, this is not something you can calculate from first principles unless you're going to do a lot of work, but it's something you have to look up. It depends on what the material is, how dense it is. It also can depend on what the frequency of the wave that's going through is. These are not fundamental constants, they're material constants. And so you have to look them up in tables in various places, and they're often in extreme amount of detail because they depend on a lot of different things. These are a few values that you'll find in your textbook. What you find is things like air, that N parameter is 1.0003. So it's very close to 1. So the speed at which the waves propagate through air is a little less than the speed of light in vacuum, but not much. By contrast, if we consider things like water, N is 1.33. If we consider things like, say, glass, it's about 1.6. Diamond is 2.4. And these are typical values for most ordinary materials. They can range from a bit above 1 to values around 3, and you can find materials that are even higher than that if you're willing to go kind of exotic. Okay, now, again, what I want to do is go through a few problems to make it clear what this index of refraction means when you consider the speed of light. So first of all, this is a very basic question I would want you to be able to understand. So in all of these materials here, just any one of them, how fast do electromagnetic waves travel? Do they travel faster than 3 times 10 to the 8 meters per second? Do they travel slower than that? Or does the answer depend on which one you're looking at? And I'd ask you to just think about that and give your answer. And what you would hopefully say is the correct answer is these objects, since all of these numbers are greater than 1, that means C is bigger than V. So V is less than 3 times 10 to the 8 for all of these materials. It's different, it has different values for different materials, but in all of these materials, the EM waves travel slower than this particular fundamental speed. Okay? Now, the other thing, just to make sure we understand this properly, in which of these materials would the electromagnetic waves travel at the highest speeds? Air with an N of 1.0003, water with an N of 1.33, glass with an N of 1.5 or 1.6, or diamond with an N of 2.4. Which one do you think has the waves that travel at the highest speeds? The answer is air, because this is the lowest value of the index of refraction. The lower the value of the index of refraction, the higher V is. And it goes the other way as well. If we want to ask which one's at the lowest speed, the answer is diamond, because this 2.5 means that the speed of electromagnetic waves in diamond is 2.5 times slower than C is. So this is the thing to understand. Making N big means the waves are traveling more slowly. Now, this N is fundamentally defined in terms of how fast waves propagate, but it's also relevant for understanding how light is refracted through materials. Now, there are things in the book that try to make this intuitive using things like lawnmowers and other things. I am not a big fan of those analogies. I don't think they're particularly helpful, because if you start thinking about them at all, it's like, well, wait, what about the light is like a lawnmower? I am just going to say that this change in the speed of light between two mediums forces a change in the trajectory of the light. It happens because, remember, these are waves oscillating at a particular frequency. The wave out here oscillates with a particular frequency, and the wave in here has to oscillate at the same frequency, or else it isn't the same electromagnetic wave that's going from one place to the other. As you try and make that work across a boundary, you need to have the direction the light travels shift or bend. And I can try and give you analogies to say why that might make sense, but I'd rather just say this is the way the world works. If you're interested, there are rigorous mathematical proofs that it has to do this, but I think those are beyond a course like this. All I'm going to say is that light passing across an interface between two materials just like has to follow a particular trajectory. Just like the light reflecting off the surface, that surface, if that surface is completely flat, it has to follow, the reflected light has to follow a particular trajectory. The light that goes into the material needs to follow a particular trajectory. So, and that trajectory is given by something called the law of refraction, or more commonly, it's called Snell's law, again, named after a guy who figured it out. So, and this law is fundamentally more complicated than the law of reflection. For any material, if you have an interface, the angle of incidence always equals the angle of reflection. That's just the way it works. When we go into refraction, now we have to care about the nature of the materials in both sides of the interface. So we have a beam of light that comes in at an angle θ1. This is the angle of incidence we talked about before. Remember, it's defined relative to the surface normal, something perpendicular to the surface. So if θ1 is big, you're coming in at a grazing angle. If θ1 is small, you're coming in almost straight. The light gets bent, and so this is sometimes called the angle of refraction or the angle of transmission. And again, it's measured from the normal to the interface. So we have an angle here that's called θ2. Now we're not calling these θi and θt here because we're going to connect them to the material properties, which are N1, V1, N2, and V2. The way the rule works is that this index of refraction times the sine of this angle equals this index of refraction times the sine of this angle. That is what Snell's law says. This is, again, something you're going to get some practice with on various problems. So, and again, this just emerges from the ways that waves interact with matter. If you have something with different indexes of refraction, these two angles have to be different. Now, because this depends on the indexes of refraction, n1 and n2, this bending angle, even if you keep theta 1 the same, will be different for different cases. And so we're going to go through a few cases to try and clarify what that means and give you some sense of what this rule tells us in general. So let's just, without calculating anything, let's just consider a few cases and try and understand what we're looking at here. Here are three different interfaces between two different mediums. We'll call the upper one medium 1 and the lower one medium 2 in all three cases, but these are different types of materials. In one case, the ray comes in this way and bends down. One case, the ray comes in and goes straight. One case, the ray goes in and bends up. I'm going to ask you to think, and I would ask you to match up. Try and do this. Which case corresponds to when the index of refraction in this medium equals the index of refraction in this medium? Which case corresponds to the case where n1 is less than n2? And which case corresponds to n1 being greater than n2? So, and we'll go through each of these. First of all, so try and do that yourself and then listen in for how I would approach it. Okay, the case where n1 and n2 are the same number. Well, if n1 and n2 are the same number, you can factor it out of this equation. And what you get is sine theta 1 is sine theta 2. The light is not affected. So in that case, the incoming angle and the outgoing angle are the same. So this case is the case where n1 equals n2. Hopefully that's not too unreasonable. What about the case where n1 is less than n2? Now, again, you can do this by solving this for sine theta 2 and doing the math, and you can feel free to do that on the problems. But look at this expression, try and get a sense of how that works generically. If these products have to be the same, but n1 is smaller than n2. So if n1 is smaller, to compensate, sine theta 1 needs to be bigger than sine theta 2. So the sine of the incident angle needs to be bigger than the sine of the transmitted angle, or the angle in this material. Now, which of these cases is that true? Remember, theta 1 is measured relative to the normal. So the thing is, and just to say, if sine theta 1 is bigger, then theta 1 itself has to be bigger. If sine theta 2 is smaller, theta 2 has to be smaller. So if this is the case, n1 is less than n2, theta 1 has to be bigger than theta 2. That's case A, because this is a bigger angle from the normal than this one. Okay, then the last case by process of elimination is this one, and it should also make sense. In this case, n1 is bigger than n2, so if n1 is bigger, sine theta 1 and theta 1 must be smaller. In this case, theta 1 must be smaller than theta 2. So if this gets deflected further from the normal, that has to be this case. So just by looking at the way light transfers through an interface, you can figure out whether the index of which one of these two things has a higher index of refraction. And there's just the answer for those of you who want it. So again, this is just pushing on the sense of getting some intuitive sense of this. Here are just, again, 3 different situations where we have a medium 1, where the light is coming in at one fixed angle, and then we have medium 2, medium 3, and medium 4. And the amount by which the light is bending is different. Here it's pretty much straight, here it's bent by a little bit, here it's bent by more. Which of these media has the largest index of refraction? Is it this one, or this one? Hopefully it makes sense that it's this one. This is the one where the bending is the largest. So this means that theta 2 is the smallest. So that requires N2 to be big. Similarly, we can do the opposite problem. Here, we're now bending the other way. One of these cases, it bends a bit. Here it's bending a bit more. Here it's bending a bit more. Which of these has the smallest index of refraction? It's this case. You might say, but wait, it bent a lot. It did. But remember, here's the thing. We're now making, in this case, remember, N2 is less than N1. So we need a bigger contrast. This means that if we want, again, you can think of it a couple different ways. Theta 2 is now getting bigger, which means N2 gets smaller. The other way to think about it is it's the contrast which determines the bending. In this case, the index of refraction of N2 is less than N1. So to bend more, you need a smaller index. So this is just to make it clear how these sorts of things work. Now, there's one place where this rule does something weird. And I do want to spend a little bit of time talking about it and building up to it. This is behind the concept of total internal reflection. It's that this rule, Snell's law, can't always work. And to see why, let's do what we would naturally do. The usual setup of a problem is, here's a medium with some index of refraction, here's another medium with some index of refraction. We send in light at some angle, theta 1. What is theta 2? That's a typical problem. How would you solve that problem? Well, you would solve this for theta 2. Now, I'm going to write it as sine theta 2 is N1 over N2 times sine theta 1. Now, you can take the anti-sign of this if you want to, or arc sign, however you want to say it, but I'm going to keep it like this for a reason. The thing is, this expression doesn't always have a solution that can work. And we're going to see when that can happen. The reason that this can become a problem is the properties of sines. Sine of any angle is always between -1 and 1. Since these angles have to be between 0 and 90 degrees, sine of theta 1 has to be between 0 and 1. Okay. Now, the thing is, this ratio, how does this ratio behave? Well, if we're in one of these situations where N1 is less than N2, so things get bent closer to the vertical, then N1 over N2, that ratio is less than 1. So you have something less than 1 multiplied by something less than 1. So the product of those, which is what's supposed to equal sine theta 2, is something between 0 and 1. There's always a value. There's always some angle that works for that. Sine of 0 gives you 0. Sine of 90 degrees gives you 1. So as long as this number is less than 1, you can always find a solution. And so this always works as long as n1 is less than n2. But if you go to the other case, things can get weird. In this case, again, theta 1 can be any angle, and sine theta 1 had better be between 0 and 1. But if n1 is bigger than n2, then n1 over n2 is bigger than 1. So it could be 1.5, it could be 1.8, it could be 2.3, it could be a variety of numbers. So you have something bigger than 1 multiplied by something less than 1. If you multiply 3 by, say, 0.7, you get a number that's more than 1. n1 over n2 could be bigger than 1. That doesn't make sense. There's no value of theta 2 that could possibly satisfy this equation, because this side has to be less than 1. So this equation will create a contradiction if n1 is bigger than n2. This rule has to apply for any wave going into the second medium. If you can't find a solution to this equation, no light can get into the second medium. This is something that gives rise to a phenomenon known as total internal reflection. Now, the thing to notice is I can make sine theta 1 really small. I could make it 0, in which case sine theta 2 is also 0. So that works. If you make theta 1 small, this is okay. But if I make theta 1 too big, this thing will break. So there is a rule. There is a particular limiting case here. So here are some diagrams showing different configurations. And typically, because people like to show air and the lower index of refraction stuff up top, this is why they're shown here this way. This is the figure in your book. So you have an incident ray. It gets bent out to be the refracted ray, and you also can get some reflection. This works as long as theta 1 is small, as long as specifically n1 over n2 times sine theta 1 is greater than 1, or sine theta 1 is greater than n2 over n1. Just divide both sides. As long as sine theta 1 is less than this ratio, you can do this. But if you make sine theta 1 bigger than n2 over n1, there's no solution out here that works. So all the light that goes off onto this interface can't refract, it has to reflect. This is what's called total internal reflection, because it means light has to stay bouncing around inside this particular material. And again, this isn't a trick or anything. This is actually, Snell's law is correct. If there isn't a valid solution, there isn't a way for light to refract into the other material. So this condition is what sets that. So you can always send the light in normal to the surface and have it pass through. But if you have it come in at an angle, there are certain angles where it can't. We define that critical angle as just the ratio of the indexes of refraction. As long as you're bouncing around shallower than that, it can't leave that material. So this critical angle, often indicated theta c, is something that just depends on the materials. And as long as you send light in at a grazing angle at sufficiently grazing angles, it will never escape that material. This is the basic principle of fiber optics. You start sending light into materials like this, and you send them in more or less straight in so they can get in, but then to get back out, they have to bounce along the surface at relatively grazing angles. And as long as you keep those grazing angles grazing enough, it's just going to keep going through the thing, no matter how, long or convoluted this is. This is the principle behind fiber optic cameras. You can basically twist these things around to an extent and the light won't escape. It'll just travel up the tube and you can see inside people or transmit data that way. So this is a fairly useful thing, and it puts immediate constraints on what kind of materials can do this. You need things with high refractive indices cladded by things with low refractive indices. So, and just to say, refractive indices is another word for index of refraction. So that's fairly useful. Of course, we have to deal with the practicalities that these are material quantities, and so you need them to have the values you want. But hopefully you're getting a sense here of how you can begin to use materials to guide light in particular ways. And we'll see a few more examples of that in the future videos. Thank you for your time.